Okay, so good morning, everyone. Um, I have checked the quiz, and maybe later I will have some announcement. Uh, I think I will explain the quiz tomorrow in the 1 hour class. So for today's class, I think we continue first. The I think this is still in last part of chapter 2, and then we are going to move to chapter 3, which is the axial deformation. And I think our course will at least have 4 chapters, so until torsion. But if we still have time, I think I will add a part about the energy. I think that is also quite important. So the energy, we call the energy method. Okay, so let's see if we can finish all chapters. Okay, so let's see the next part of our lecture is the extensional strain. So we have defined from the previous results, there is the definition for the stress and strain, and we start from the stress, which we call the supposed to true stress, and how the shear stress and the normal stress works, and how it also affect the inertia. Okay, if you remember, we include the inertia property in our calculation and in whole formula within this part. So we are not only see the materials or the object as just a simple object now, but we need to also include the inertia, okay, based on the mass or height on this specific subject. And we get everything here calculated, finding the force, moment, using the centroid, and based on the inertia. And then there are some examples also how to find the stress resultants. And this is one way. And now we are going to get the definition of the extensional strain. So remember that the extensional strain is the change in length. Change in length of a line segment divided by original length. If we suppose that we write in terms of illustrations, and so we can illustrate some, let's say the original body, the undeformed body as the left part, and we say that we are going to have the direction n, and so we start to look at the point P, okay, and then when we take the direction n, we take some infinite small line segment of the length delta s. So in between PQ, we have the delta s in direction n. And then if we take the infinite small line segment PQ for that delta s, and then after deformation, the PQ, if you see this part here, it becomes an arc. So from straight line, it becomes arc, okay, with arc length delta s asterisk. Okay, so we may write this changes. Okay, this changes the delta S. The delta S after deformation minus the original delta S divided with delta S, and then based on our definition, then the extensional strain at point P, so this will be, we can write this as the extensional strain at P in direction N, we could write as the E for the strain with subscript N P. Okay, that's the idea. And the definition is taken by the limit. So as Q getting closer to P, along with the direction N, it means that Q and P getting closer, or we can say Q is getting close to P, which means that they will get into getting closer to 0. Okay. Now, if we see from other illustrations that we are starting to have, I think, quite proportional picture, that we have the like plate. Okay, if we have a plate A, B, C, D, so this will be a square plate that is thin, and then it will go some deformation in which no point in the plate displaces in the y direction. So we are going to focus that the deformation will be on the x direction. So every horizontal line in the plate except line AD is uniformly shortened. So we are going to make sure that the AD stay as it is, stay as the same original length, and then the other horizontal line will getting shortened. As we can see from the picture, you see that the AD here is still the same AD as before, but the rest of it, they are getting shortened. And the AB remains straight and rotates clockwise. So AB, it's getting shifted, but it's still remains straight. It's not deformed into arc shape. So that's the question or the example given. So how to determine the strain in x? Okay, remember that we have the definition for the strain for some direction n. This will be the definitions. So we could write the same limit calculation or limit equations. So we can say that we have the strain for x in x direction as limit as delta x getting 0 and the delta x and delta x asterisk, we are going to see that both of them, they are defined in the figure. And if we look at, just to make sure that we're clear, we can take Q, perhaps Q is here, and there will be a new Q, maybe here, that is going to be defined. So this PQ we define as the delta x, and the P asterisk Q asterisk, that is the delta x after deformation. So first we can write an equation for the delta x. I think, let me write here. So the delta x asterisk, because the delta x asterisk, it says that it is going to be shorter than the original length. So the delta x should be minus with something, right? Should be minus with something. And we know from the picture, we have that this will be 0.2a. So we can take this as a geometrical shape. So right here, that's the original one. So that's 0.2a. And the original length is a. And the sides for the square is a, right? Okay, so suppose that we have a we say this is y. So let me write here, maybe here. So BC is shortened or shorter than the original BC by 0.2, right? 0.2 or 20%, right? 0.2a. Okay, so it's 20% of a. And then the shortening of horizontal lines will be linearly related to the straight or the vertical line, which is the y, right? So we could say that the delta x asterisk is the delta x minus y over a. Geometrically, we can write this, multiply with 0.2 delta x. So this is just to say that this is going to be the 20% of the original a. Okay. So the strain will be limit as delta x getting 0 of the delta x. Since delta x asterisk is delta x minus this statement, then this will be canceling the delta x. So this will be negative y over a, 0.2 delta x over delta x. And we can see that we can cancel delta x. So the strain will be negative y over a, 0.2. Okay, so basically we are just using the geometrically shape from the gradient. You can say the gradient here. So we have the gradient, so y over 0.2a. Or you could say this is supposed to be this gradient here. Okay. And you will see that the answer is having the negative signs, which means that it's true that we have the strain shortened. Okay, so the negative, it means that indicates shortening. Okay, so that's the uh, definition for the extensional strain. But basically, pretty much all the strain, either the extensional strain or later we are going to see the shear strain, they are going to be based on mostly by the geometrical shape. And by geometrics, it means that it means that whenever you have some review or discussion on this, then you need to connect yourself to some geometric perspective, either perhaps the gradient or perhaps the triangle ratio, as in your quiz. You need to take the triangle ratio for the force distributions, and then you will get the formula for the shear force and the moment. Okay. Later I will deliver your quiz in the break time. Okay, anyway, that's the extensional strain. And the next part is going to be the shear strain. Okay, it's not extensional strain, it's shear strain. Okay. As we mentioned, I think in the previous subtopics on the shear strain, then the true or the more general way to describe the shear strain is by taking the body deformations, and then perhaps we are going to have some point. Let's say we have 3 points R, P, Q. So we observe the PR as direction T and PQ as direction N. Okay. And then there will be some deformations in which this line PR and PQ, there will be some changes, which means the straight line will become an arc, and then the angle in between these two lines will be changes. It will be changed. So, and then this, and remember, every time we are observing something like some elements like this, it means that this line PR and PQ, they are a very, very small elements, or we could say an infinite small element, and we define that as this limit. So we can say that the Q getting closer to P along this N directions, and then R getting closer to P along to the T directions, and we take the angle pi over 2 minus the new angle. That is the shear strain, how the angle changes, like how far the angle changes in between these two lines. That is the definition for the shear strain. So basically, if we make it into some example, like the similar with the previous extensional strain, like for example, here we have a plate, square plate. We have a PR, PQ, the same points as we mentioned, and we take note that the PR is delta Y, PQ is delta X, and then we have all the units for X, Y, and then the origin length is A by A for the sides, and then we take some deformation, and we can see that after deformation, all the points are changing, and then well, you could imagine if you have like a toys for kids, like if you know Slinky, you can imagine that we can make it displace the like a toys like this, if you know, right? If you played with this one before. So imagine that this will be slightly, or right, with the slightly displaced to the left like that. So you can see that it has some slight changes. So it could be illustrated as it is, although our topics here is a plate. Okay, so but you can imagine through your toys like that. Okay, so we have slight changes in the angle. So the angle pi over 2, it's become this theta asterisk. Okay, so as we mentioned here, how far the angle changes, that is our shear strain. So we can write that the shear strain, or the using this gamma, and we observe through this point P, or we could just say in point XY, and then the theta will be pi over 2 minus, okay. Now, the best way to describe, is by taking the point, for example, we have the m, okay, x m, or this is the x, okay, the x distance from A to M, and then assuming that, so this is assuming that that will be the same x, the same distance for the xm, that will be the same distance, and then we have another distance that if we are going to take as the xn asterisk. So we are going to have this, if you could see that this is, we can make a triangle here. Okay, so we have this triangle, or let me draw a triangle there, please. Wait. Okay, that's this triangle, right? And that angle, the one that we want to follow, is basically, we can simply write as the tangent inverse of the xn minus xm over A. Okay. So we can write this within this calculation here. Let me write here. And then what is xn? Xn is, if we could see the idea, this is the original. So the original length for the xn is just the same with the am, the xm, with the, which is the x distance at the same length. So we start with the x plus. Okay, we are doing the same thing as previous one. So we have some additional length here. And then by taking the same formulations, because this is supposed to be the same with same with a previous example, which is we have this one here is the 0.2a, okay, 0.2a. So we are going to have the same relations and calculations for this 1 minus x over a, multiply with the 20% of a. So the xn minus xm, basically we are just canceling the x, which we have the 1 minus x over a multiplied with 0.2. Okay, and then therefore the angle theta asterisk become pi over 2 minus tangent inverse, and then we replace all with the 0.2, 1 minus x over a. And the lines act in x and y, they are going to remain straight, so the theta will not depends. So theta does not, in this case, in this example, doesn't depend on delta x and delta y. So this will be just the tangent inverse 0.2. Okay. Okay, I think that is the last part on chapter 2, which we are going to review more in the next exercise. But I think for now we could go first to the next chapter, the axial deformation, just to get in some introductions, and then on the review parts we're going to deal that with the Tuesday class. So every Tuesday class, as usual, we are going to have more exercise and practice. So I think I will prepare another additional works for you, and also additional works for I will have assignments for you, at least to add your quiz results, okay? Because your quiz averagely not very good, so I will give you some assignments, and hopefully from that assignments and some review, you have some basics for for the statics, at least the equilibrium parts, how to get the sigma f, sigma m equals 0, and how to write down all the formulations, okay? Okay, let me go straight to the to the next chapter, which is the axial deformation. So let me start with the definition, okay? So we say the structure have, or it is going to have the axial deformations when loads applied to member or subjected to temperature change, or let me just write delta T. And then we say the first idea, axis, or I think let me just using this one. Is this already concluded here? Okay, so we say it will be there is axial deformation when loads or some changes in temperature. The axis of the member means the structure member. Okay? The axis of the member remains straight, and then the cross sections, which are plane and are perpendicular to the axis, it will remain a plane. So it will be, so if we have the like a straight bar, if you make it longer, if you cut the bar, the cross section is still the same, and the cross section is still the same. And then the cross section do not rotate. Okay, it's not rotate, so it's still on the same straight axis. So if we could see here, the cross sections, it's still plane, and then it is still straight. It's not going to be bent. Okay, it's not going to be bent. So this is the basis and all the assumptions. Okay, all the assumptions within the topics. Okay. So we call this is the kinematics assumptions. Okay, kinematic assumptions. Plane, and then remain plane. So before deformation and after deformation, remain plane. And then cross section do not rotate about the axis. Okay, that's the emphasis. Okay, this is the picture. And then how we could see the differences and how we write the deformation itself. It's by taking this strain. Okay, so this is the strain, the final length, just similar with what we have in the chapter 2, but we are going to analyze in a more detailed, minus initial length divided with the initial length. So we say this distance, which is going to be the displacement of the cross sections. Okay, if we have this, okay, this is this. We can say the displacement at the cross sections A. This will equal to, we say, displacement. This is displacement ux. So our goal within these topics, by taking the strain relations, is to determine what will be the formulation for this ux, the displacement. Okay. Okay. Now the first thing is, by taking the strain formulations, using the limit in this x-axis, then if we take changes in terms of the ux and delta x. So delta x will be the changes in the axis, and then ux is the displacement. Okay. Now we are going to have the axial strain. Okay, the axial strain is basically the differences on the ux. over dx. So we call this axial strain. Okay, this is what we call the axial strain. So strain at one axis. Okay, strain at one axis. Or in mathematical terms, we can say this is du dx, or derivative. Okay, this is derivative, or we can write, maybe if you could see clearly, this is exactly this, d dx of ux. Okay, so ux is if we could maybe brings ux as a function of x, then the definition for the strain will be the derivative of that ux. Okay, this will be or this term is also called a strain displacement equation. And if we want to emphasize what is this about the strain displacement equation, we could also observe the distributions, okay, as in this picture. So this will be axial or a strain distributions. Okay, so this will be strain distribution. So if we want to maybe rewrite what is this about, so axial deformation it will be characterized by the extensional strain that is not a function of position in the cross section, which means we only care about the end end points, okay, or the two ends. Okay, so the total, so which means the total elongation will be E equal UL minus U0. Basically, that is the elongation. And then if we take the sum for every changes on every small increments in the member, in the elements, for the entire length, let's say at the length L, then we get the integrations formula. Okay, we are going to get the integrations from 0 to L of the functions axial strain. Which basically that's the same thing. Okay, it is the same thing. So to simplify what this is about, then let's see here. So we have the before and after deformations. Okay. Suppose that we have some deformations in the x-axis, and we only have, for every subtopics in this chapter, we are going to have only one axis that is going to have a change in the deformation. So the elongation we only have in one axis. Okay, let's say usually we take the x-axis, that's the one that is changing. So we start by the initial point A, and we take that as u at 0, and then we define a function u as a function of x. So every part of x we can evaluate, and then we have the initial length L. Okay. So then the the idea is, if we take the displacement for each one of the elements, and then if we observe the after deformation, we could see that there is a change in the length, which we see that the A will be a new point A asterisk, B is the new point B asterisk, C also the same, and then the length, the total length will be L plus some elongation, which we define from the elongation formula. So what this is actually about is basically, this is not as simply, oh, we see this, oh, changing this part. Okay, this is the change, but what this is elongation about is basically we say that in every increment here, there will be small changes, and we take the small changes, we plus all of them, and we take that as elongation. So that's what it means. So we have the L plus E, which is E is actually how we sum up everything through the x-axis. Okay? Although, if we see analytically, it seems like we are going to take a really detailed and perhaps a little bit complicated, but actually we are going to see that we can model this, and then we can have a oversimplifications, and that will be our method to deal with the axial deformation. Okay? So from this part, we are going to see in another perspective, we also have the what we call the material behavior. So, and we are going to limit this behavior only for linear. So case will be linearly elastic behavior, which means that we are going to have the Hooke's law, okay? Which means the Hooke's law is for the x-axis, we could write, okay, I hope you can see the differences. This is the E for the Young's modulus, and this is the E for the strain, okay? So this is the Hooke's law will be applied. And there will be some subtopics on what will happen if there is some nonlinear behavior, but I think I will skip that part. Okay? So we are only going to focus on the linear elastic behavior. So your case will be simplified and supposed to be modeled very very clear. Okay. And then another behavior is members are homogeneous. Homogeneous mean E will be constant. So we have the homogeneous uniform distributions. Okay. Now another thing, the stress resultants. Okay, the stress resultants. The stress resultants, as we can see from the stress resultants from the picture here. So we have the bending M, the force X, and then if we take the small elements and then write the definitions throughout all the system within the body, the diagram, Then we have the F is the integrations with respect to A, sigma dA, and then the my is Z sigma dA, and mz is y sigma dA but negative. Okay. Okay, I think we can. Okay, so for the part of this stress resultant on the case of the axial deformation, although we start with observation that we have the F, M, My, and Mz, we're going to see that at later proving for this formula, we're going to have a really simple formula for I think for calculations, and we are going to use that as our analysis. So first, maybe before that, do you know why this is negative? Am I told you why it's negative? Anyone know why is this negative? Do you know what this moment in physics? Like usually in your, like you have, if we say the, oh, sigma moment is, what was those moment? So we have this x, this is maybe some f, and this is a, this is b, this is c, so maybe this is the x over 2. If we say the sigma moment is 0, we need to first set up the point of view, right? Which one is we are going to take on? Okay. For example, we take on this part here, and let's say we have let's say f1 is f2, which means that we have the f, and then we take to that point, right? And if we, well, we could make positive, negative based on your preference. We can say this is positive, or we can say this is positive. Same result, because every time we take this and consistently with all the same respect, the our setup, they are going to have a consistent value, whatever your choices. So that's it. Let's suppose that we have this, which means that this f2, and then this is x over 2, so f2, x over 2, right? And then this is another one, which is still positive. This is 0. Okay, so we have some relation between f1 and f2. Okay, now, this is in terms of already in the sigma and the A. Actually, how we define the moment is actually from the axis. We are going to then look using the right hand. Okay. So for example, here's the F, and then we have the y is here, z is here, so y is going up, z is going there. So mz, we get mz is going to be y and then f. So it's supposed to be y and then f. It's supposed to be go there, positive one. But here we make it on that point, which means the opposite direction. That's why it's negative. Okay. So right hand rule. Okay, right hand rules. Okay, now from this stress resultant, and since we have the Let me write again, homogeneous, and then linearly elastic member. Then we can have the modulus for the Hooke's law. Okay, so we have this in this stress distribution, the E is constant, the modulus. Okay. And since E is the constant, then stress distribution will be also constant. So this stress distribution is constant over the cross sections. And then we could say that here, whenever the normal stress is constant, then we can make our simplifications for all the stress resultants. Okay. Let me write here some some simplification. So ZDA, we're going to take this as a centroid Z bar A, and then for the Y, the same thing, we are going to have the Y bar A. And then if we choose the x-axis, okay, if we choose the x-axis, so if choose x-axis, so the axial deformation passes through the centroid, which means all the centroid Y bar will be equal to Z bar will be equal to 0. And because of the 0, then the My equal Mz equals 0. Or if we write in some conclusions that if we have a constant modulus, okay, Young's modulus, then the member will undergo or will have the axial deformation if the applied load is axial force that is going to pass through the centroid. And this will be, I think, very important assumption that in the next problem or the next case, we're going to have most of the problem will be having this kind of problem. So the deformation, we're going to simplify and assume that it will going to pass through the centroid. So we only care about the deformation on the centroid here, on the center. So the axis will be assuming on the centroid, so that we could only focus what will be the elevation, what will be the displacement. So that's the idea. So we are going to simply have a good model, and by good model, it's quite simple, easy to use, and it will be having a good impact and predictions for our calculations. Okay, that's good model. It doesn't always need to be exactly correct in like in numerical, but it can predict whether our displacement is really huge or really small. Okay. So this will be the assumption. So this will be important for our assumption here. Important assumption. So E is constant, and then axial deformation the force is passed through centroid. So then by taking these assumptions, then we take the distributions loading, and we are going to take the equilibrium for the x-axis. Okay. Now, if we look at the picture, the figure, so we have the axis symmetric. Okay, we call this is axis symmetric axial loading. So let me write here. This is the axis symmetrical loading, which means that they are going to have some value per unit length. Okay, like the distributions in the chapter 1. Okay? So we have the px, and then if we are using the free body of the infinite small length delta x, so we are going to have like a small displacement or small element delta x as in the picture here, this delta x. So we cut in slicing this member as the distance delta x. Then we take the limit to define our f. For the equilibrium, we are going to have, this will be the definition for derivative, right? This is derivative definition using limit. So this will be the definition. So definition will be d dx of the f of x equal negative px. Which we can integrate this to give the axial force, right? So we can also, it can be also integrated like that. Okay. But it's still in the integrations. It's not it's not easy to follow. So if you have any formula that it still has some integrations or perhaps some derivative operators, then it's still not a good formula or good model. The good model, if you are having really perfect formula, and you have, well, the good model is if you have perhaps exactly linear model without any symbols for integral or derivative, and then perhaps the more simple, the more small the model is, that is a good model. Now, this part we are going to summarize. Okay, all this part we are going to summarize. So first is the axial stress formula. This is the axial stress formula. Okay. And then we have the axial strain. And this is really important here. Okay. And then, so this is, I will say this is important. And then we can write from these two cases. Okay. from the axial stress and the axial strain, we are going to summarize these two in terms of the elongations. But we still have the integration. We were going to define with some exact length that we are going to define here. So this is we call the axial force deformation equation. And then by taking the dummy variable, okay, taking t as dummy variable, or taking it to another parameter. So we can write the E, or maybe E is elongations. Let's write in terms of displacement U. So U of x is U of 0 plus this okay, U is displacement, this is initial, let's say initial length or displacement. Okay. Now we are going to now focus on this elongation formula that we are going to see in the next subtopics. Okay. So suppose that we've taken the L for our X, we can write E just to let you know what we are going to have. This will be F, and the X will be X, so it will be L, and then this will be A, and this will be E. So fly. Easy to remember, right? Easy to remember the formula. Even you don't need to write the formula. So this will be the, I think for the whole case in the axial deformation in chapter 3, this will be our main formulations. Elongations equal F multiplied by L divided by A, and then E as the modulus of elasticity. The difference is, I think there will be some cases that we call statically determinate structures, and the other one is statically indeterminate structures, which we are going to see that maybe in the next few weeks. But now we are going to focus on this one here. And let me just take some overview for what we have now. So first is we call the uniform axial deformation element. Now we have the picture here. So if a members, okay, if, let me write here. So if members that first is have constant cross section or A, and then 2 have constant E, which means it's linearly elastic, and then 3 have axial force applied only at ends. we say that if we have this, then we call this is the uniform axial deformation element. So this will be satisfied if we have a constant cross section, constant linear elastic, or a constant modulus Young, and then half axial force that is applied only at ends. Now, if we see the figure, first is we have a hanger, and then we have links, numbered links, 1, 2, 3 on the right side. They are both, I think, it's uniform axial deformation element. So if we see, this could be only having at the ends, right? And then we could see that perhaps that will be, there will be a some deformations. And the second picture also, if we see the spring and we have a slider block that is going to take in some forces over there, then this is also a case where members are axial deformation element. Okay, and let's simplify it. Okay, let's simplify what this is about. So let's simplify it. Let's suppose, so simplify the methods. So we are going to see the elements here. We have the F at the ends, at the two ends, and then we can write the free body diagram. So we slice this member to get into the free body diagram, which we have the Fx and F. And then using the equilibrium that is sigma F for the x-axis equals 0, and we can simplify that the sigma F or the F will be the same through all the points, or this will be a constant F. And then we can write that this will be taken into that, and this will be the elongation FLAE as we observe from the previous page. And also it can be written, and I think as long as you know the first one here, this one, it's supposed to be sufficient. Okay. The other alternative, this or that is just some cases for some cases that need to be analyzed throughout the other characteristics. Okay, for example, we can write in terms of the the F, the small f, where the small f the LAE, or we could write in terms of K, which K is AEL. The F we called, so F is the flexibility coefficient. And K is stiffness coefficient. But most of the case, these two coefficient is not needed. Okay. But for analysis, sometimes they requires us to know the coefficient. But most of the time, we only care on the axial deformations, the elongations. What is the displacement, the final displacement. Okay. Okay, I think for axial deformations, I will just getting through up until here. I think let me go through the your quiz, I think, so that I can prepare some assignments for you. So let's go through this. I think this is your quiz, right? Okay. So for the questions related to the whether we have the force, sometimes we could say every force maybe that is on the straight axis or the horizontal, maybe we could say, all right is positive, left is negative. But that is not the correct analogy. It's not always like that. So the best way to describe is if you have perhaps your result is negative, but you assume maybe it's on the left. That means if it's negative, it means the right. Okay? You get that? So I think that's better way to assume. So my suggestion is you have negative and then you have the picture. You need to write the conclusions. Where's the direction? Left, right, up, down. They just write up, left. Okay. So it's not just calculate how much is it, but also which direction it should be. And then this is the AX, because I think that is the easiest one to see. You have 4.4 kilometer, 13.3 kilometer, and then you have the only that external forces that is going into the horizontal line. And then we have A and B pin. That A has the horizontal, with B there's not. So it's easy to see that we can use this AX for that 4.4 and 13.3, which we have the 17.7 to cancel out that's those two. Well, actually, like if you are maybe intuitively familiar, well, you have external force going to the right, so it must be a reaction force that cancels out, which you see that it's supposed to be go there, right? But I'm trying to prove that, okay, let's just assume over right. But my result is negative. So that means it's not right, it's to the left, right? Okay? So right directions to the left. Okay? And then to get the reaction at B, and also I think the AY, we have it here, AY. So we need either way, like if you try the sigma moment first, you try the fx, fy, just write all the possibility equal 0. Well, sometimes like perhaps when you write this and then you get the idea for the vertical force, okay, we think we have this, And then how do I know this one? Okay, perhaps from the other equilibrium. Okay. So from any directions, you are going to get everything. And you are going to get everything. Okay, of course, I started out with the fx because I believe that is the easiest way to find. But actually, you can start from here or here. Maybe if you start from the fy equals 0, you will maybe stop here for a while. Go back here, oh, we get something here, and then go back here, take the sigma moment with respect to A, and then remember, we can have options. Either we are making the force in line with our moment structures, or we take the structures in line with the force. Both ways may be okay, but sometimes one another will be, maybe the other one will be easier and the other one will be more complex. But it should be the same result. Okay? I'm taking the 1.8, I will make that axis y, okay, as vertical. So I will multiply with the sine. Okay. So that is the 7.7, which is the AX. And then 7.7. Oh, the 7.7 is the 13.3 and 4.4, that part. And then I will rotate this, go through that A, which means this is having a vertical here, right? Remember that every force in physics you can move around. Move around as long as it is on this under the same distance. You can move around. You can force basically no distance as force. It has only direction. Right? So you can move around. So you can move this 7.7, go there, and then use that for y. Okay, this distance y. So that's this one. Okay, and then we have this 22.2. Okay, it's easy to see. Okay, that way. I will make on my perspective is the clockwise is positive. And then By, this, go there. Okay, 1.8, 1.8, 3.6. Okay. Compute, we get 80.76. And because that is the one that I wrote here as going up, it's staying positive, then this is positive. If this result negative, then it will be down. But I don't think so, right? Why? Because the external force is going down. So you should have a reaction that's going up. Okay, logically. So you could like expect the result. You could expect the result. Okay, the result will be this. And then we have this, By. We have the Ay plus By equal that 22. So we have Ay. So we get everything, right? Okay, I think no problem here, right? Okay, and then now I think the difficult part is the second one because it's going to be the internal forces, which means you need to decide which one is compression, which one is tension. Okay, I think most of you forget to write whether it has a compression or tension. Okay. How to know? The same with the previous. Every time we have the opposite, then okay, maybe there will be a compression because I think by default we see the force as going out as tension. When we get okay, it's coming back, then it will be a compression. So we take because we want to know 1, 2, 3. This is 1, 2, 3, and I add another point to help B and C just to helping the calculation. We isolate BCD. Okay. By isolating this BCD, I will have a forces that I will call this F2 here, and F2 will be here. Okay. So then I will have this only. So I will have only the 13.3, 22.2, this F2, and I will make this F4 here, and then we have. Actually later we are going to say F5, but still now I will just only having this BCD. So that's the first part. Taking the sigma moment, since there is a lot of F here, I will take the moment at this point first to get at least this f3. Okay. We know by, and then we know that we can make this the vertical distance from the sine, okay. And then taking the equilibrium, we get everything, and then this is going to be negative. So f3, that is, I assume it's going to be outside like that. It's not, which means that it's compression. And then I think we could go the Fy. The Fy first. If we only observe the okay, we only observe on this point here, the definition for the vertical is only this, and that, right? So we have this taking to the vertical line, and then we could write and get the F2. We could also take another point or another isolation. So we take these isolations. Now we have F4, F2, F5, F1, and then 22.2, and then we are going to isolate everything here. Or we take the equilibrium to get the F4 and F5. F4 we get from the sigma Fx. F5 we get from the vertical F1. Okay. So we can, so in the statics we can isolate everything as long as we make some limitations. Okay. For example, we take this. Okay, we only care about this. Okay, because this is basically they are going to take it as 0, right? And then we get everything from the F5, from that, and then from the F4. Okay. I forgot to write but if we still have time, let me write just some few points for the second question. Okay, let me copy the picture first. Okay. Okay, the second question is basically, first is analyze the expressions on the distance AB. In between, so it doesn't mean exactly at this. So it should be here, x. So x can be this, as long as this is going to be 0 to 150. So the expected result will be in terms of x. So you have like a function. It's not a constant. The second question is exactly at b, which means you have the number. So the expected outcomes will be a constant. Okay. So that's I think important. If you know the outcome, the expected outcome, you know how to, like, if you get the result and then you feel, oh, this is a little bit strange, that means you need to evaluate your answers. Okay, let me go through here. Let me put out the picture. So this will be, so first is about the x to 150. So we need to cut. Okay, we need to cut. So let me draw. Okay, let me draw this. And suppose that we taken this. Let's say we taken this. Okay. Okay. So maybe let me write a little bit smaller, just to make sure that this is going to be x. And we have the distribution forces. Along this x distance. Okay. Okay, now we see this will be 7 Newton per millimeter. Okay, so this will be 7 Newton per millimeter. Okay, let me just write. That's the same height, right? Same height for the forces. And then we could write the resultants. Okay, remember, if the triangle is your resultants, then it will be, the distance will be this, okay, this distance. This will be x over 3. And this will be 2 over 3x. Okay, the distance. It's always 1 over 3 and 2 over 3. Okay. And this will be 7 multiply with wait. This is not 7. This is not 7. I forgot to mention the results. So this is 7, right? This is 7. So this will be I think let me draw it here. You need to draw like this, because that is not 7. 7 is this, and that one is here. Suppose that this is y. Okay, this is y. This is x. Okay. And the 7 will be 150. Okay, do you get it? Okay, so y, or 7 over 50 is equal y over x. So y is 7 over 150 multiplied with x. Okay, so that's your y. So this part here, is 7 over 150x. So the resultants will be 7 over 150x multiplied with x over 2. That's the resultants. So the equilibrium will be sigma f y equals 0. And if we take this is going to be the v1, this is the f1, and this will be the m1, right? So taking everything, 7 over 150 x squared over 2, or over 300, is equal, since they are both the same direction, so this will be negative 7x, suppose v1 is negative. Okay, and then the same thing with the sigma m. And let's say this is the x. Let's say this is the x, okay? Since that is the x distance, so I will get that for the moment with respect to x, the view. So, and I will take this as a positive sign. So I will have negative multiply with x over 3 and then we have negative also m1 equals 0. So m1 or m1x is equal negative 7x cubed over 900 Newton millimeter. This is Newton, this is Newton millimeter. So this is V1 and this is M1. Now the resultants on section D, let me add another picture to help. So we take, since we see from the two pins, we only have BY and CY. So let me just write here BY, sorry. And this will be CY. Then we can take, for example, if you would like to calculate CY, we could take the sigma M with respect to B to get CY. Okay. And you can take the other one, the other way around for the other part. But I think this one will be practically better. Oh, this one has the roller, right? So we have another CX here. And you can calculate using the 7 Newton over millimeter, and then with the distance 150 and another 150. So this will be exactly at the middle. This is 150 Newton at 1050 Newton, and this will be 5 to 5 Newton. I think most of you correct for this one. This is going to be 100. This is 50. Okay, and then taken everything. So this will be, let's say, if taken that is 0. So negative 525. And then multiply with 50. And then plus 150 multiply with 75. And then negative CY 150 equals 0, and you can calculate and get CY is around 350 Newton. Okay, now what this CY will be it will play as a supporting role. So if we imagine the segment DC, then we can only focus on this diagram. So we have CY, we have CX, and we are going to have this is VD, FD, the one that we're looking for, and MD. And then doing the same, and I hope you know how, and I believe most of you getting this correct. So taking sigma Fy equals 0, sigma moment with respect to, let's say this is going to be the D. So at D is 0, and then we get everything for the part. Okay. Because we know that this will be 75 millimeter, right? Okay, so we get everything, and I think if you calculate the equilibrium, you get the VD is 175 Newton and MD is 6562.5 Newton millimeter. Okay. Okay, I think I will complete this and give you later on. Okay, I forgot to write the second question. Okay, I think that's it for today's class. We are going to have a more exercise tomorrow, and I will upload some assignments this week maybe tomorrow or Wednesday I will upload.